laws and everything. But when you take ideal gas mixtures, a mixture, each of the components of the ideal gas mixture are separately treated as independent ideal gases, and the laws are applicable to those separate independent ideal gases. So, as a whole, when you try to apply the ideal gas laws, you have to apply it in a bit different mathematical treatment.
Bhavana, Bhavana Devi, Bhavana Devi. Can you tell what are the laws you come across in ideal gas mixture? Anybody studied so many laws? What are?
Dalton's law of partial pressures,
Huh.
and one more can be Dalton's law of partial pressure, and
So in ideal gas mixture, we have three laws, mainly Avogadro's law, Dalton's law of partial pressure, and Dalton's law of additive values. Okay, Dalton's law of partial pressures state that the total pressure of a gas is equals to the summation of partial pressure of individual
of the
gas.
individual gas.
Similarly, we are having Amagat's law. You remember scientist name called as Amagat's. Amagat's law of additive volumes. Okay, the total volume of an ideal gas is equals to the sum of the volume of the individual gases. Okay, that is called as Amagat's law of additive volumes. I derived all the derivation also. In the exam, they may ask, okay, did Dalton's law partial pressure?
But sir, I had a question.
Tell me. Ask
If
me.
you consider if you consider ideal gases to be made up of particles which are point particles, basically the volume of each of the molecules of the ideal gas is negligible. It is infinitesimally small,
Mm,
and if the volume of each of the molecules of an ideal gas is infinitesimally small, then the
mm,
volume of the net ideal gas, considering their intermolecular is only dependent on the intermolecular space between these molecules. Yes or no?
yes, yes, correct. Okay, correct.
Yeah. So now, if you bring in another ideal gas, okay, if you bring
Mm,
another
mm,
ideal gas and if you diffuse it into this ideal gas, you are
okay.
introducing, suppose
Mm,
you did it in a closed container. What you are doing basically is you are introducing some other point particles into this mixture of point particles, right? So already there were point particles in the cylinder, and
mm,
you brought in some more point particles of a different gas, and you introduced it into this cylinder, okay, at the
mm,
same conditions of pressure and temperature, of course.
mm,
Now let us say after diffusion, whatever intermolecular space was there between the point particles of the original gas in this cylinder, in that
mm,
intermolecular space itself, some new point particles have been introduced. Okay.
correct,
If this is
correct.
the case,
Mm,
even though we have introduced new point particles in the intermolecular space of the original gas, since these
mm,
new point particles also have negligible volume, okay,
mm,
so it
mm,
does not
mm,
affect the gas on a whole. So we see that
mm,
the volume of the combined gases is actually equal to the original volume itself without making any
mm,
great changes.
mm,
So in this
correct.
case, how will you apply the law of additive volume?
No, additive volumes comes into picture whenever the volumes are taken into consideration. Then only it is applicable. Okay. If the volume is negligible, in that case, it does not hold good. Okay. It should have a certain value. Okay. It should have a
Yes, sir.
consideration for volumes. Then only it holds good. Okay.
Like
Additive
if you
volumes.
take, even if you
Ah,
take real gases and if
mm,
you put
mm,
them at a very, very high pressure
mm,
and
mm,
sorry,
mm,
very, very low pressure and very, very high temperature, okay,
mm,
so
mm.
then they are going to behave almost like ideal gases.
Real gas,
And the
correct.
intermolecular space between them also will be very high compared to the
Mm,
intermolecular space. The
mm,
volume of individual molecules will be very less. So if I
mm,
bring another real gas at the same in the under the same conditions and introduce it, diffuse it into this
mm,
uh, real gas, which is at low
mm,
pressure and high temperature, then again the total volume after this diffusion will continue
Mm.
to remain the same as it was originally, but
Correct.
we will not see any changes in pressure and temperature either, right? So
Correct. Correct.
in
Mm.
that case again, the additive volume law doesn't hold good, right?
Correct. 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 Okay.
So
So
I think
additive all.
in
Tell me.
the upper regions of the atmosphere,
Mm.
where the
Mm.
pressure is really low and the temperature is pretty high,
Correct.
I think there we can see this phenomenon, right?
Correct, correct, correct. Okay, correct. What
So
I said,
these
no,
were the
correct.
questions I had.
Correct, correct. What I said, exactly right. Okay, the additive volumes, the Amagat's law of additive volumes comes into picture whenever the volumes of individual gases are taken into consideration. Then only it holds good. Okay.
Yes,
Okay,
sir.
if it is very small, okay, infinitesimally small, in that case, it does not hold good. Okay.
Yeah, and
Does not
I
hold
think
good.
the most important condition is that the sum of the two interacting gases,
Hmm.
uh, the resulting mixture should also be at the
Hmm.
same pressure and temperature. Otherwise, if you
Hmm.
want to maintain the same volume, I think pressure will go up, right?
Correct, correct.
If you add up just like
Hmm.
that.
Correct, 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 correct.
Yeah.
So do remember that additive law of that Amagat's law of additive volume holds good only you are going to consider the volumes of the individual gas. If it is negligible, then it does not hold good. Okay. Mm.
Yes, sir.
Okay. Today I'll do the revision on ideal gas mixture only because you are having this chapter for third internals. You are having the ideal gas, real gas, and the availability part. Okay. For third internals. Hope you understood all the concept, all the laws, derivation. Okay, derivation mainly concentrate on van der Waals the equation that is P plus A by B square into B minus B equals to RT, and you concentrate on the problems related to the real gas. How to see the compressibility chart. Okay, how to see the chart which consists of the reduced parameters and the chart you are going to use is to find out the values of A and B for van der Waals equation, etc. Okay. And also already you know how to use the steam tables for a pure substance chapter. Okay, one is a temperature based table and another one is a pressure based table. And in pressure based table, the units are in bar. You do remember? Okay. Sometimes they'll give in the numerical problem, particularly they'll give in kilopascal. Okay, suppose 100 kilopascal. Don't go for 100 in the steam table. So you have to first convert the 100 kilopascal into the bar. So then only you get the correct answer. I'm telling you, the conversion of unit is most important. Okay, concentrate mainly on the units. Okay, suppose 200 kilopascal means you are searching 200 means in the steam table it is wrong because the whatever values they are given they are in bar, but here in the problem they'll give in the kilopascal. In that case, there will be difference. So first you have to convert in bar, then according to that value, you have to find out enthalpy, sensible heat, total heat, and then everything, entropy, etc. Then you have to find out the properties. That's why I'm telling you, units are most important while solving the problems. Whatever chapter you take, either model 1, 2, 3, 4, 5. Okay, the units are most important. So you have to put proper value in your problem, then only you'll get the correct answer. So now today I'll do some numerical problems on ideal gas mixture. Okay. See, I'm doing only one problem. Okay, so if this is a problem, it includes everything. Okay, so you come across the ideal gas problem. So during polytropic process, what is the change in pressure, volume, etc. Now I'm going to do one problem on ideal gas mixture. A mixture of ideal gas consists of 2.5 kg of nitrogen and 4.5 kg of carbon dioxide at a pressure of 4 bar and temperature of 25 degrees Celsius. Determine the mole fraction of each constituent. Okay, though we studied mole fraction. So the mole fraction, it is the mole of individual gas to the total number of the moles of the gas mixture. That is nothing but mole fraction. Like that, we're having mass fraction and volume fraction, etc. Mass fraction is the ratio of the mass of the individual gas to the total mass of the ideal gas mixture. Like that, we're having the volume fraction. Volume fraction is the ratio of volume of the individual gas to the total volume of the gas mixture. Here, they are given mixture of ideal gas consisting of 2.5 kg of nitrogen and 4.5 kg of carbon dioxide at a pressure of 4 bar and temperature of 25 degrees Celsius. Determine first part is mole fraction of each constituent, equivalent molecular weight of mixture. We studied two gas constant. One is general gas constant and second one is the universal gas constant. General gas constant R is difference of Cp and Cv, and R equals to R bar by M. R bar is your universal gas constant and the value is 8.314 kilojoules per kg Kelvin and divided by molecular weight. Okay, molecular weight of carbon is 12, hydrogen H2 is 2, the molecular weight of O2 is 32, that is 16 into 2. You remember certain gases. Okay, equivalent molecular weight of the mixture. Next, equivalent gas constant of the mixture, the partial pressure and partial volume, the volume and density of the mixture, the Cp and Cv of the mixture. Means this is the one problem which includes everything. Okay, if the mixture is heated at constant volume of 35 degrees Celsius, what will be the changes in internal energy, enthalpy, and entropy of the mixture? As I'm telling, so in order to find out the internal energy, enthalpy, and entropy, you should have the idea of first law of thermodynamics and second law of thermodynamics. Once you analyze these laws, then only we can understand this concept, that is changes in internal energy, change in enthalpy, and change in entropy of the mixture, and also determine the changes in the same properties when heating is done at pressure. Okay, so and they are given gamma is 1.285 for carbon dioxide and gamma is 1.4 for nitrogen. And remember, gamma is always 1.4 for air. Okay, it is 1.005 divided by 0.78 ratio of specific heat Cp by Cv. So gamma is always 1.4 for air. In this problem, they are given the gamma for individual constituent. As I said, the ideal gas mixture is the one which is a mixture of the constituent gases. Here in this problem, there are two constituent gas. One is nitrogen and second one is carbon dioxide. And as I said, first part is you have to find out the mole fraction. Mole fraction is the number of the moles of individual gas divided by total number of the moles of the ideal gas. The first, we are going to find out the mole fraction of nitrogen gas. Mole fraction is represented by mu. Mu is a Greek word. Okay, so in basic thermodynamics, the mu is mole fraction. In fluid mechanics it is dynamic viscosity, like that. According to the concept, we are utilizing the symbol. Okay, in basic thermodynamics, mu is our mole fraction. Mu1 is the mole fraction of nitrogen gas equals to the number of the moles of nitrogen gas divided by total number of the moles of the gas mixture. Okay, so the number of the moles, sorry, this is first one, mass fraction. So what I'm doing is, it is a mass fraction. So 2.5 divided by 28. 28 is the molecular weight of the mm, nitrogen. We are getting a 0.0892. Okay, so first you have to find out the number of moles of nitrogen gas. It is given by 2.5 divided by molecular weight of nitrogen, that is 0.08. 2.5 divided by molecular weight of nitrogen is 28. You get 0.0892. And how to find out the total number of the moles of the gas mixture is, first the number of the moles of nitrogen gas plus the number of moles of the carbon dioxide gas. How we are finding out 2.5 divided by 28? Like that, we are going to find out the number of the moles of the carbon dioxide gas. It is 4.5 divided by molecular weight of carbon dioxide gas is 44. How will you get 44? 12 plus 32. So to find out the total number of the moles of ideal gas mixture, first one is 2.5 divided by 28 plus 4.5 divided by 44. So this is the total number of the moles of the ideal gas mixture. You remember, okay, so mass fraction is different, mole fraction is different. Mass fraction is just the mass of the individual gas to the total mass of the ideal gas mixture, whereas the mole fraction is the number of the moles of the individual gas to the total number of the moles of the ideal gas mixture. So the total number of the moles of the gas mixture is 2.5 divided by 28 molecular weight of nitrogen plus 4.5 divided by 44. You get 0.191. Now we are going to find out the mole fraction of nitrogen gas. Mole fraction of the nitrogen gas is the mole number of the moles of nitrogen gas is 0.0892 divided by total number of the moles, that is 0.1915. So you get 0.4657. This is the mole fraction of the nitrogen gas. Similarly, we have to find out the mole fraction of carbon dioxide gas. How to find out mole fraction of the carbon dioxide gas? The number of moles of carbon dioxide gas divided by total number of the moles of the ideal gas mixture. So number of the moles of the carbon dioxide gas is nothing but 4.5 divided by 44. Remember, you have to take this part. The number of moles of carbon dioxide gas is 4.5 divided by 44. It is nothing but 0.10227 divided by total number of the moles. Already we got it as 0.1915. So the mole fraction of carbon dioxide gas is 0.53. The first part to find out the mole fraction. Sometimes they may ask mass fraction. Mass fraction is very simple. That is the mass of individual gas to the total mass of the mixture. Okay. Now the equivalent molecular weight. To find out molecular weight of the mixture, so you have to multiply. This is the mole fraction of the individual gas multiply by molecular weight of that particular gas plus the mole fraction of the second gas multiplied by the molecular weight of the second gas. Just you have to multiply and sum up, will get the equivalent molecular weight of the ideal gas mixture. So mu1 already we got, that is the mole fraction of the nitrogen is 0.4657 into molecular weight of nitrogen is 28 plus the mole fraction of carbon dioxide is 0.534 into the molecular weight of carbon dioxide gas is 40. So after solving, we are getting the equivalent molecular weight as 36.535 kilogram per kg mole. Okay. This is the second part. First part is to find out the mole fraction of individual gas. Okay. Next, second part is equivalent molecular weight of the mixture is whatever the mole fraction multiplied by molecular weight of first gas. And unit is most important. It is 36.535 kilogram per kg. Now, third part is to find out the equivalent gas constant of the mixture. We have to find out separately the gas constant for nitrogen gas and gas constant for carbon dioxide gas, and then we have to sum up. That gives your the equivalent gas constant of the mixture. First, we have to find out the total mass of the gas mixture. That is mass of the nitrogen plus mass of the carbon dioxide gas. Mass of the nitrogen is 2.5 given in the problem. Mass of the nitrogen is 2.5 plus mass of the nitrogen is 4.5. So you get the total mass of the mixture as 7 kg. Okay. Now to find out the characteristic gas constant for the gas mixture as like this. Okay. That is mass fraction, mass of the nitrogen gas multiplied by the general gas constant for nitrogen plus the mass of the carbon dioxide gas multiplied by the general gas constant for carbon dioxide divided by total mass of the gas. Using this one, we can find out the equivalent molecular weight of the mixture. The rating is m into r into plus m c2 into r c2 equals to r into m. Okay, like that you can find out. So based upon that equation, you can take capital R. This capital R indicates general gas constant of the gas mixture. Okay, it is nothing but mass of the nitrogen gas multiplied by general gas constant of nitrogen gas plus mass of the carbon dioxide gas multiplied by the general gas constant for carbon dioxide gas divided by the total mass of the mixture. Okay. So M is mass of the nitrogen gas, that is 2.5. And as I said, the relationship between R and R bar is R equals to R bar divided by M. So R bar is always, you have to, R bar is nothing but universal gas constant, and its value is always 8.314 kilounits. 8.314 divided by molecular weight of nitrogen is 28 plus 4.5, that is mass of the carbon dioxide gas is 4.5 multiplied by general gas constant of carbon dioxide gas is 8.314 divided by molecular weight of carbon dioxide gas, it is 44 divided by total mass of the mixture, means 2.5 plus 4.5, we get 7. So after solving this one, R is 0.2275. Okay, you remember we assumed the value of R as 0.287 while solving the problem. How you get a 0.287 means 1.005 point minus of 0.7 may you get 0.287. Okay, you see when they are given particular value, so in that case we are getting the general gas constant for the ideal gas mixture as 0.2275 kilojoules per kg Kelvin. This is the third part. First part we found out the mole fraction. Second one, we found out the equivalent molecular weight. And third one is the equivalent, the general gas constant for the gas. And fourth part is to find out the partial pressure and partial volumes of the gas mixture. Okay. So how to find out partial pressure of the nitrogen gas and partial pressure of the carbon dioxide gas. Partial pressure of nitrogen gas is the mole fraction of nitrogen gas multiplied by the pressure of nitrogen gas. You see, the pressure of nitrogen gas is given as 4 bar. Okay, see, 4. Okay. You see there in the problem they are given at a pressure of 4 bar. What you are going to do to find out the partial pressure of nitrogen is the number of moles of nitrogen gas multiplied by given pressure. You see in the problem that is mu into, that is a mole fraction. Mole fraction for nitrogen gas we obtained as 0.4657 multiplied by the pressure. Okay, that is 4. We will get 1.862 bar is the partial pressure of nitrogen gas. Okay, we have the Dalton's law of partial pressure. We have the Amagat's law of additive volumes, Avogadro's laws, characteristic gas equation in ideal gas mixture chapter. Okay, next to find out uh, pressure, partial pressure of carbon dioxide gas is the mole fraction of carbon dioxide gas multiplied by the pressure of the gas. Pressure of the gas is given 4 bar. Just you have to multiply with the mole fraction of carbon dioxide. The mole fraction of carbon dioxide we obtained as 0.534 multiplied by 4. We'll get PCO, that is partial pressure of carbon dioxide gas is 2.136 bar. Now you see, we are going to apply the ideal gas equation. Okay, PV equals to MRT for nitrogen gas, whatever gas it is there. So we have to apply the ideal gas equation, PV equals to MRT. Or our aim is to find out the volume of the nitrogen gas. It is nothing but MRT divided by P. So M is mass of the nitrogen gas is 2.5. R is, once again you have to take R bar divided by M. And here you have to convert the units in terms of joules only. Otherwise, you can express in terms of kilo units. That is also correct. Kilopascal, but you have to maintain the same unit. Here, 8.314 into 10 to the power of 3 that is joules per kg Kelvin divided by 28 molecular weight of nitrogen into temperature. Temperature is 25 degrees Celsius is given. You have to convert into Kelvin. Why you are converting Kelvin means the unit of R is joules per kg Kelvin. Suppose you are putting the temperature in degrees Celsius, your problem become wrong. That's why you have to express the value of T in terms of. So it is the volume of nitrogen is 2.5 into 8.314 into 10 to the power of 3 divided by molecular weight of nitrogen is 28 into temperature is 25 plus 273 divided by 4 bar. 4 bar you have to convert in 4 into 10 to the power of 5 Pascal or 4 into 10 to the power of 5 Newton per meter square. You remember 1 bar equals to 1 into 10 to the power of 5 Pascal or 1 bar equals to 10 to the power of 5 Newton per meter square. So after solving this, we are obtaining the volume of the nitrogen as 0.553 meter cube. Similarly, we have to find out the value of volume for carbon dioxide. Apply the same formula, but change the value of m. That is mass of the carbon dioxide gas is 4.5, and you have to change the molecular weight of carbon dioxide gas. And remaining, you take that temperature and pressure is same. So for all the individual gases. To find out the volume of the carbon dioxide gas, so MRT divided by P for carbon dioxide gas. The mass of the carbon dioxide gas is given in the problem as say 4.5, and R for carbon dioxide gas is R bar divided by molecular weight of carbon dioxide. R bar is universal gas constant, that is always 8.314 into 10 to the power of 3 joules per kg Kelvin divided by molecular weight of carbon dioxide gas. Carbon dioxide gas is 44. Temperature is 25 degrees Celsius or 288 Kelvin divided by the 4 bar. It is nothing but 4 into 10 to the power of 5. So after solving, we are getting the volume of the carbon dioxide gas as 0.6334 meter cube. Next, we now what we found out, this is the volume of the individual gas. One is the volume of nitrogen, and second one is the volume of carbon dioxide gas. So next, total volume of the mixture is given by V equals to MRT divided by P. M is total mass of the mixture. Total mass of the mixture is 4.5 plus 2.5. So you have to take 7 into R. R means we have to take the equivalent general gas constant. We found out in second part that equivalent gas constant is given by 0.2275. Don't take individual because we are going to calculate for the entire gas mixture. In that case, you have to take the general gas constant for the entire gas mixture. It is 0.2275. So the total volume of the gas mixture is given by V equals to MRT divided by P. So M is 7, that is 4.5 plus 2.5. R is R bar divided by M, that is 0.22975 is the equivalent molecular weight of gas mixture into 25 degrees Celsius, 25 plus 273, it is 298 divided by pressure of the gas is 4 bar, it is nothing but 4 into 10 to the power of 5 Pascal. After solving, we are obtaining the volume of the gas mixture as 1.188 meter cube. And next part, you have to find out the density of the mixture. Okay, you understand this problem carefully, because in this problem we are going to calculate everything: mole fraction, mass fraction, general gas constant, universal gas constant, the partial pressure, partial volume, total pressure, total volume, everything. So this is the one problem which covers the entire thing. To find out density of the mixture, okay, we know that density is mass divided by volume. So mass is nothing but total mass. Means 4.5 plus 2.5, you get it as 7. and divided by, you have to take the total mass of the mixture. Okay, don't take individual here because we are going to find out the density of the gas mixture. Density of the gas mixture is mass of the gas mixture divided by volume of the gas mixture. Okay, so mass of the gas mixture is 4.5 plus 2.5 divided by what we got, the total volume of the mixture as 1.18. So we are getting it as 5.892 kg per meter. Next, we have to find out the Cp and Cv of the mixture. Okay, that is specific heat at constant pressure and specific heat at constant volume of the mixture. Specific heat at constant volume. So you remember this formula, R equals to Cp minus Cv, and Cv is nothing but R divided by gamma. So how you are getting this equation means you have to divide throughout by Cp. That is Cp by Cp is 1. Sorry, you have to divide throughout by Cv. Cp by Cv minus of Cv by Cv is nothing but 1 equals to R divided by Cv. So you'll get Cv as R divided by gamma minus 1. Remember, starting you have to write this equation, R equals to Cp minus Cv, dividing throughout by Cv, that is Cp by Cv is nothing but gamma, minus Cv by Cv is nothing but 1, equals to R divided by Cv. So from that one, we can write Cv as R divided by gamma minus 1. Okay. So once again, R is R bar divided by M. First, we are going to find out for nitrogen gas, R equals to R bar by M. That is 8.3144 divided by molecular weight of nitrogen is 28 into gamma minus 1. As I said, gamma, you have to assume it as 1.4. Okay. They won't give the gamma value in the problem. You have to assume the value of gamma as 1.4. Next, so Cv equals to R divided by gamma minus 1, that is 8.3144 divided by 28 into 1.4 minus 1. Remember, the value of gamma is always 1.4. Standard gas air. For Cv, we are getting it as 0.742 kilojoules per kg Kelvin. This is the unit of Cv. Next, we have to find out the value of Cp. Cp is specific heat at constant pressure. So you have to use this formula, that is Cp by Cv equals to gamma, or Cp equals to gamma into Cv. So gamma is 1.4 and Cv is what we obtained it as 0.7. So we are getting the Cp for nitrogen gas as 1.0388 kilojoules per kg. Now, in the same way, we have to calculate the value of Cp and Cv for carbon dioxide gas, and they are given for carbon dioxide gas in the problem. They are given gamma as 1.285, so don't assume 1.4. 1.4 for air. Okay, in the problem they are given gamma is 1.285. Okay, for carbon dioxide gas, same value you have to take. So gamma is 1.285 and Cv, specific heat at constant volume is, it is a ratio of R divided by gamma minus 1. R is R bar divided by M. 8.3144 divided by molecular weight of carbon dioxide gas is 44 into 1.285. 1.285 is the value of gamma for nitrogen, carbon dioxide gas given in the problem. So after solving, we are getting Cv as 0.663. Then you apply the formula Cp by Cv equals to uh, gamma. So Cp equals to gamma into Cv. Gamma is 1.285 for carbon dioxide gas into whatever value we got. This is the procedure to find out the value of Cp and Cv for carbon dioxide gas. Next, we have to find out the Cp and Cv for the ideal gas mixture. So this is the formula you have to use. Okay. MCP uh, nitrogen. Okay, the product of mass and Cp for nitrogen gas plus mCp into carbon dioxide gas divided by mass of nitrogen gas plus mass of the carbon dioxide gas. Okay, so mass of the nitrogen gas is 2.5. The Cp for nitrogen gas is we obtained it as 1.0388 plus mass of the carbon dioxide gas is 4.5 into Cp for carbon dioxide gas is 0.8519 divided by the mass of nitrogen gas plus mass of carbon dioxide gas. So after solving, we are getting the Cp as 0.918 kilojoules per kg Kelvin. Similarly, we have to find out the Cv of ideal gas mixture. Okay, instead of Cp, just you take Cv formula. The MCV N2 plus MCV U2 divided by mass of nitrogen gas plus mass of carbon dioxide. Mass of nitrogen is 2.5 into Cv for nitrogen is 0.742 plus mass of carbon dioxide gas is 4.5 into Cv for carbon dioxide gas is 0.663 divided by the mass of nitrogen is 2.5 plus mass of carbon dioxide gas is 4.5. So we are getting Cv of gas mixture as 0.691 kilojoules per kg. Okay. Next, to find out the change in internal energy. As I said, the internal energy is uh, its standard formula is mCv into delta T. Whatever process it is, you have to use this standard formula only. U2 minus U1 is nothing but delta U. Delta U is mCv into T2 minus T1. M is mass of the mixture. 7 and Cv is specific heat at constant volume is 0.69 and you should take this value of the mixture you have to take into T2 minus T1. Okay, initial temperature is 25 and the final temperature is 35. So you'll get 48.37 kilojoules. That is the change in internal energy. And one more thing, sometimes you may get negative answer also. So positive value indicates the increase in the internal energy and the negative value indicates the decrease in the internal energy. Okay, next part is you have to calculate the change in enthalpy. ಈಗ ತಗೊಂಡ್ರೆ ಪೇಪರ್ ಹಾಕ್ಬೇಕಾ ಇದು ಸಪ್ರೇಟ್ ಅಂದ್ರೆ ಅರ್ಧ ಪೆಟ್ರೋಲ್ ಇದೆ ಪೆಟ್ರೋಲ್ ಪೆಟ್ರೋಲ್ So change in internal energy is given by U2 minus U1 equals to mCv into T2 minus T1. Okay. So M is mass of the gas mixture 7 kg into Cv, that is specific heat at constant volume for gas mixture you have to take. Okay, that is 0.691 whatever we got now into difference in temperature. And similarly, you should remember these two formula. One is change in internal energy and one is change in enthalpy. The change in internal energy is given by mCv into delta T and change in enthalpy is the product of mCp into delta T. Okay. This standard formula you should use. Okay. For whatever ideal gas is there, ideal gas mixture is there, the standard formula. One is mCv delta T and one is mCp into delta T. So M is mass change in enthalpy is given by mCp into delta T. M is mass of the ideal gas mixture 7 kg. Cp is specific heat of gas mixture. What we got is 0.918 into difference in the temperature. So we are getting the H2 minus H1. H2 minus H1 is nothing but delta H. That is 64.26 kg. And change in entropy formula. Okay. So as I said, the change in entropy formula. So change in entropy is given by I derived all the derivation. Okay, so you have to use the general derivation. Okay, so which involve the entropy change in terms of temperature and volume. Like that, I derived the expression for the temperature and pressure and volume. But which equation you are going to use in this problem is the entropy change in terms of temperature and volume, because it is V1 and V2 is given T1 and T2. Anyhow, V1 and V2 gets cancelled because the V1 and V2 are same, because it is a constant volume process. So you have to take only the first part. Okay, if it is constant pressure, you have to use temperature and pressure, whatever equation you are having. That's why I said, so go through the derivations of entropy change properly. Once you understand all the equation, do remember that equation, and then you are going to apply that equation in this problem, whatever it is, ideal gas or ideal gas mixture. The same formula holds good. So S2 minus S1 equals to mCv into ln T2 by T1. Anyhow, V1 and V2 are same. So those term will get cancelled. Okay. Okay. So you have to substitute. M is mass of the gas, that is 7 kg. Cv is specific heat at constant volume of the gas mixture, 0.691, and Ln T2 by T1. So you have to take the temperature in Kelvin. Okay. So you get the answer as something of whatever answer you're getting, you have to put that answer. So this is how to solve the problems. Okay, so this is the one problem. Try to understand here. This problem we are going to solve all the things. Okay, so it includes the first law of thermodynamics, second law of thermodynamics. Means we are learning entropy in second law of thermodynamics. That's why I'm telling. Once you analyze first law, second law, and entropy, so then only this module 5, that is ideal gas mixture and real gas mixture, so becomes easy. Okay. So such kind of the problem, it may carry 10 to 12 marks. Okay, because we are going to find out every parameter in this problem. And sometimes instead of constant volume, they can use constant pressure also. So the same formula holds good. Only in entropy change, you have to change the equation. That's it. Remaining is the same procedure. So understood this problem, students? Any doubts? Okay. Try to concentrate on numerical. Okay. So because in thermodynamics, in each question you are having two bits. One A, one B, means one A carry your derivation or definition. Okay. And in second bit, definitely it will be a problem. That's why I'm telling you, concentrate mainly on the problems. Try to solve more number of problems. Okay. So then only you'll get the confidence. Try to solve more number of the problems in all the chapters. You'll get confident. Please, all of you enter your equation in the chat box without fail for
Sir,
attendance purpose. Tell me,
so can you post the model for notes and
model,
plus model for notes, sir?
model for notes.
Yes.
Uh, okay, then I'll post it. Ideal guess and real guess mix. I'll post it.
Okay.
PDF file, I'll post it.
Okay, sir.
Any other things you want? Like, any
Sir,
other?
portions
Uh,
is ideal gases and real gases only, right, sir?
no, actually, some more question is there, that is availability here. Little bit, not too much.
Okay.
What is availability? What is non-availability? I have done some one or two derivation. No,
Yes, sir.
that part I include, because that part are not included in the second test. Little
Okay, sir.
one question will be there, one or two questions. But concentrate mainly on this ideal gas and real gases.
Okay, sir.
Any other things you want to ask?
No, sir.
Uh, I'm telling you, in thermodynamics, practice is most important. You have to work a lot. Like you are having many derivations, many concept, many laws. Okay, to see the thermodynamics data handbook charts, etc. That's why concentrate properly, try to do well in the exam. Okay, I'm telling this module 5 is easy. Okay, compared to other modules, this module 5 is easy. Okay, hardly you are having some 4 5 derivation and remaining only the concept. Okay, once you understand the concept, you can solve any number of the problems. But basic concept is most important. So please, all of you enter your revision. All of you entered, right?
Yes, sir.
Please, all of you enter. Okay, so do well in the exam. I'll share the case study this material soon in the Google Classroom. Okay, thank you, students. Okay. I'll stop the session now.